I want to take you through another Coulomb's law calculation, but this one's going to be a bit more two-dimensional. So let's start off. I'm going to draw this nice and big so you can see all the detail. Let's have charge 1 here. We'll let that be negative. Q1 is equal to negative 86 microcoulombs. So we've got charge 1 right here. Let's go over here a bit. Let's say some distance away, charge 2 can be positive. Q2 can be equal to 50 microcoulombs, and some distance up will be charge 3, also positive, and Q3 can have a charge of plus 65 microcoulombs, or positive 65. All right, so let's close this triangle off. And you know what? For mathematical simplicity, let's go ahead and make this be a 30, 60, 90 triangle. Now, Coulomb's law doesn't take angles into account. It takes distances into account. So I have to actually put some distances in here. 30 centimeters for there. And if this is a 30, 60, 90 triangle, 30, 60, 90, then that would make this be 52 centimeters, and this 60 centimeters. That's rounded, of course, but that is going to be the situation that we are in. And let's calculate the net force on charge 3. So just like before, we need to find the force. It's going to be the sum of the force between charges 3 and 2, and the force between charges 3 and 1. Okay, and so let's just go ahead and find those. I think I might be able to fit them here. I think I can. I'm going to give it a shot. Let me just give myself a little boundary for the sake of organization. Let's see if I can keep it straight. All right. So the force of object 3 on object 1, bearing in mind it's, K times Q3 times Q1 over the distance between 3 and 1 squared. So let me just fill that in. K is 9.0 times 10 to the 9th. I'm going to leave the units off this time. Q3 and Q1. So we've got, I should use parentheses, 6.5 times 10 to the negative 5th. That would be 65 times 10 to the negative 6th, but adjusted to be in proper scientific notation. And here we go. 8.6 times 10 to the negative 5. So we've got K, Q3, Q1, and we need to put R squared in the bottom. So that's going to be there. Okay, so just to be clear, there's K, Q3, Q1, R squared. And what do we get from this loveliness? We get 140 newtons. Okay, so that is okay, that's in frame. that's that force. That's the magnitude of it. And that's an attractive force because this is a negative charge and that's a positive charge. So that means there is 140 newtons in that direction on charge 3. All right, let's do the same thing for charges 3 and 2. Okay, so I've got a little bit less room. I think I can manage. So for the force of object 3 and object 2 being K, the charge of object 3, the charge of object 2, and the distance between objects 3 and 2 squared. Oh boy. So that's going to be 9.0 times 10 to the 9th. There's K times the charge of object 3, 6.5 times 10 to the negative 5th, times the charge of object 1, 5.0 times 10 to the negative 5th. And that is all over 0.30 squared. Okay, so what's that going to end up equaling? 325 newtons. And that would be the force of charge 3 and charge 2 on each other. That's repulsive. So that would be, on object 3, a force of 325 newtons in that direction. Okay, so we've got 2 vectors that we need to add together. Okay, let me go ahead and add another border to this. I think I'm going to have to switch to another page here in a minute, but I want to keep everything up as long as I can, but divide it up so it doesn't get overwhelming. There we go. So here's what I've set up for myself for the next page. The force between charges 3 and 2 has a magnitude of 140 newtons and a direction. Remember, it's down that way. So I could call that negative 30 degrees, or I could call that 330 degrees. If I were in class, I would ask you which one you prefer, but since I'm not, I'm just going to have to make one up. So I'm going to go ahead and say negative 30 degrees. If you preferred 330 degrees, I don't know, you're just going to have to let me know, I guess. All right, so we've got that force, that magnitude, that direction, and then the other force, that would be, here we go, between charges 3 and 2. It has a magnitude of 325 newtons and a direction, well, it's repulsive. I mean, that's not a comment about the physics. I'm saying it's pushing it away, and it's doing it at a direction of 90 degrees. Okay, so on the next page, I'm going to combine those two forces. We need a new direction and a new magnitude. So hopefully you didn't forget how to add vectors. Let's get to it. Okay. So if I were to draw something representative of this, let me draw charge 3 here. So there is a force in that 90-degree direction with a magnitude of 325 newtons, right? So here's my, imaginary 0 degree mark. So there's 90 degrees. And then I have to add to that this force right here, which has a magnitude of 140. That's less than half of that. Something like that. 140 newtons. This cute little 30-degree angle. Isn't it so adorable? Okay, so those are the two forces, and we need to add the two of them up. You could complete the triangle and use the law of cosines, but, nobody got time for that. So let's do it component-wise. Remember, this is the force between charges 3 and 2. This is the force between charges 3 and 1. So I'm going to have to get an X component for that force and a Y component for that force. Well, this one's super easy because this is a strictly vertical force. So it has no X component, and the entire thing is the Y component. Ta-da! Okay, let's do the other one. For this one, we need to find an X component and a Y component. Now for the X component, we would be multiplying the cosine of this angle by that magnitude. Now the cosine of negative 30 is the same as the cosine of positive 30. It's the square root of 3 over 2. And that means that if we multiply the square root of 3 over 2 by 140, we get a nice approximate 120 newtons. So that's the approximate horizontal component of that force. Okay, as for the Y, we'd be looking at the sine of 30, except this would be negative, pointed downward. The sine of negative 30 times 140. The sine of 30 is 1/2, so this is nice and easy. It's negative 70 newtons. Okay, so to be clear, this force has no X component. This is the only force with an X component, which means that when we add them together, this will be the X component. So whatever this force is, it's going to have 120 newtons as its X component. Okay, what about for the Y component? Well, this has a lot of vertical, 325, and this one only comes down half of 140, that's 70. So 325 minus 70 is 255. All right, so that would be the X and Y components of the resultant vector over 120 up 255. That looks a bit like this. Let's see, I want to make sure I get this right. Sure, yeah, like that. So oops, I'm a little out of frame there. There we go. So here's 120. Here's 255. Okay, so that's the vector itself. Let's find the magnitude and the angle. So the magnitude, of course, is going to be Pythagorean theorem, the square root of 120 squared plus 255 squared. And that's 280. So we can go ahead and label that. And what about the direction? For this one, we're going to have to do the inverse tangent, the arctangent of the opposite over the adjacent. So here we go. The inverse tangent of that is about 65 degrees. Okay, so if we go back to the original question that was posed, these three charged particles, or these three charges in these locations, what is the total force on this? Well, the total force on that is 280 degrees in the 65-degree direction. Okay, that right there is how you would calculate the total force on a charge given some other charges. You need to use Coulomb's law to calculate force vectors. Then you add the vectors together. There's your answer. Okay, there are more complicated calculations that we can do, but you know, there's only so far and so hard I want to push, especially in circumstances like this. So I'm thinking this is going to be as difficult as the math is going to get. All right. If you have any questions, of course, reach out, email, all that kind of good stuff. But for now, that's all.